Hi guys, Harry here. Welcome to Scrap Science. So in a previous video I showed you how to make one of these gelatin salt bridge membranes for electrochemical experiments, and then in this video I'm going to show you, using this thing, how to make sodium hydroxide from the commonly available chemicals of table salt or bicarb soda, or what I'm going to show you first is soda ash or sodium carbonate. The first thing you're going to need is 2 containers. I find that solo cups work really well because when we need to put the membrane across, we can just stick that over there and it fits very nicely. What you'll need to do next is you need to get some water and just put maybe around 100 milliliters in each container. I'll get that done. So you can see I've filled the cups with just enough water so that this membrane, when we put it in, the salt bridge just dips in to both sides and can so act as our ion conductor in the electrolysis reaction. I'll get a bit more into what that all means later in the video. The next important piece of the setup are your electrodes. Now for the anode, this is the positive electrode that we'll be connecting to 12 volts. It's an absolute must that you have carbon or something like platinum or gold. Carbon seems to be the easiest to get, just graphite rods, even pencil leads will work pretty well. I take these carbon rods out of zinc carbon batteries, found in like old lantern batteries. Now I've put this carbon electrode together with 3 rods, and I've just wrapped some copper wire around that and connected it all up so we can make a connection here. When you dip it into the water like this, you want to make sure that the parts that you've wrapped with copper are not actually touching the water, because the copper will interfere with the reaction. You just want this the carbon bit down here to go into the water like that. Now for the other electrode, the cathode, or the negative electrode, you can actually use pretty much any common metal other than aluminium in order to do the reaction, seeing as aluminium will react with the sodium hydroxide that we make. I've made this in the same way that I've made the anode. I've just wrapped some copper around a carbon rod. You don't have to use carbon, like I said, but I think it's more convenient. Now the reason that you've got to use carbon as an anode is due to the fact that this is the electrode where oxidation is going to be taking place. So any metals that you use other than noble metals or carbon, even carbon will oxidize to carbon dioxide eventually, but all common metals will tend to just corrode and oxidize. Whereas on the cathode, so this is the electrode where reduction is taking place, so any metals that you use will be absolutely fine. They won't corrode or anything. In fact, if you use a rusty piece of iron, then all the rust will flake off and it'll actually clean it. Now for the next step, you're going to need some kind of sodium salt. Any sodium salt will work for this, though using different ones will give you different byproducts of the reaction. So what I'm going to use first is just a nice easy one, sodium carbonate. It's a pool chemical that I can get pretty easily. And so what we're going to do is put that into the anode chamber. Of course, the cheapest and easiest sodium salt to get would just be sodium chloride or table salt. However, using this one will actually generate chlorine off the anode, and if you're not in a well ventilated area, or if you're doing it outside, then that's not really ideal. However, with sodium carbonate or sodium bicarbonate, the byproducts will just be oxygen and carbon dioxide coming off the anode, so not much of a problem at all. Now I forgot to mention it earlier, but just in case you didn't want to watch the video where I made this gelatin membrane, all it is a U-shaped tube that I've made out of, there were milk carton handles I think, and I've filled up this U-tube with vegetarian gelatin. You can't use normal gelatin because that'll degrade really quickly, but vegetarian gelatin, it's nice and easy to get. It works really well as a non-permeable membrane for electrolytic reactions. So I've filled this up with the gelatin and mixed it with just a little bit of salt to make the water in there conductive between the 2 chambers. Of course, the salt that is in the actual membrane will lead to just a little bit of chlorine coming off the anode, but it's so minor that it's not really something to worry about. Now that sodium carbonate doesn't seem to be dissolving very quickly, so we'll give it a bit of a stir. Could even take the electrodes out in the salt bridge to make that a little bit easier. So I'll give that a stir till it all dissolves. It won't matter if it doesn't all dissolve, seeing as it'll all be used up in the reaction anyway. So at this stage we're pretty much ready to start. We've got our anode in this, I call it the left compartment, with our, I think it's called an analyte, that's filled with sodium carbonate. We've got our salt bridge, and we've got just regular distilled water over here with our cathode. So the only thing left to do is to connect it up to power. Now for my power supply I use the 12 volt line off an old computer power supply. You can use any real power supply for this, even batteries will work, or just regular AC chargers that you plug into the wall. I like to use a computer power supply, seeing as we've got access to 12 volts, 5 volts and 3.3 volts. I won't use 5 or 3.3, seeing as 12 volts will get the reaction going a lot quicker, but it's always an option. Now to actually turn one of these on, if you've got one, you'll actually need to get a little jumper wire and find the green wire, you can see it just there, and connect the green wire to the black wire with your little jumper, and that should turn the power supply on. See, I don't know if you can see, but I can see that that fan is turning now, meaning that the power supply is on and good to go. So now remember, we'll connect up the cathode to the negative part of the power supply to 0 volts, and we'll connect the positive electrode of the anode to 12 volts. I'll actually put in my multimeter in series so that we can measure the amount of current that we're getting. So now I'll splice the multimeter into the circuit. We've got 12 volts coming in here, got a little switch to turn it on, connect it up. That's going into the multimeter, and then the multimeter goes into the anode. We've got the actual reaction taking place, and then the cathode we've got going back to 0 volts. So if we switch that on now, we should see a little bit of current. There we are, 1.5 milliamps. That's not very much. Now the reason that we're not getting very much current just yet is due to the fact that we have just distilled water in our cathode chamber, which isn't very conductive at all. So while there's a very low current, we'll start to generate just a little bit of sodium hydroxide on the cathode here, and that will make this chamber a lot more conductive, and we'll get a much higher current. But in the meantime, I might grab a couple of 12 volt batteries to put in series, get it up to 36 volts, and then we'll get the reaction started a little bit faster. So I've put the batteries in series so that now we have 36 volts going into the cell. We'll turn that on and we should see a fair bit more current. Our 5 milliamps to start off with, and we should see that ramp up quite a bit as we start to generate sodium hydroxide in this chamber. So it's been less than a minute and the current has slowly risen. We're getting there slowly, but I don't know if you can see, but on the cathode right there are just some tiny little hydrogen bubbles rising up to the surface, which means we are generating sodium hydroxide over this side of the chamber. Excellent. So the current's kind of slowed down at around about 68, 69 milliamps, and we're at the point now where you can kind of start seeing little bubbles, if I can get the camera to see, there we are, little bubbles of oxygen and carbon dioxide coming off the anode there. And if we have a look at the cathode again, you can see that we're getting quite a few nice hydrogen bubbles, showing that we're generating a fair bit of sodium hydroxide. I'll leave this running for an hour or so. When you do it, you can run it to completion by, you can kind of tell that all the sodium carbonate hasn't dissolved for me, but by the time the reaction's done, all that sodium carbonate will have dissolved and be used up in the reaction to generate sodium hydroxide over here. If you really want to run it till the end of the reaction, then you can get a piece of pH paper and dip it into the anode chamber, and once it reaches a pH of 7, then you'll know you've used up all of your sodium carbonate in the reaction. So we'll let that just react away, and I'll be back in an hour. So it's been an hour, and since then I realised that one of the batteries has actually nearly gone flat. It was only giving out around 6 volts, so that was a bit worrying. I put it on the charger, and we're now just stuck with 24 volts across our power supplies. We've got 62 milliamps flowing through the cell. I was expecting more current, around twice that amount, but I think it might be due to the fact that sodium carbonate isn't really a very conductive solution. When we a little bit later on, when we try sodium chloride, I think that the current will be much higher than 62 milliamps, but we'll find out then. So now that it's been running for a while, so we've still got some nice hydrogen bubbles off that electrode. We can check the pH with some pH paper, and we should see, yeah, look, that's right off the scale with pH paper. Very basic, indicating that we do have sodium hydroxide. If we compare that to, if we measure the pH of this one, yeah, so you can see it's not quite as basic as the sodium hydroxide, meaning that that's really what you'd expect from sodium carbonate solution. I think I'm going to stop the reaction here. It'll just take too long otherwise, because I can still see, I don't know if you can, just a little bit of sodium carbonate in the bottom of that, meaning that we've still got a fair bit of sodium ions to transport over to the other side of the reaction, and I don't really want to wait that long, so I'm going to stop this one here, and we will maybe try with some sodium chloride. There's also no smell of chlorine coming off the cell, so obviously the chloride content of the salt bridge wasn't very high. If you do actually think there's going to be a bit of chlorine coming off the cell, don't test it like that. Shouldn't have to explain why. So I've disassembled everything, and we've got our nice clean sodium hydroxide solution in this cup over here, and what remains of our sodium carbonate from before. You can kind of see there was, when I took the salt bridge out, it kind of got a little bit damaged by the reaction, as they do. They don't last very long, but a little piece of it just there fell out into that chamber, which is a little bit annoying. It's also a little bit discoloured due to tiny little particles off the anode have just kind of dispersed into the water here, making it a little bit dirtier. But that hasn't happened on the cathode side because the electrodes haven't been corroded. So now I was going to set up the second test with some regular table salt to try to turn into sodium hydroxide, but then, seeing as I live right next to the river, maybe I should go down and grab some seawater and see if that works. That way it's a free process. So I'm down at the beach now. We'll grab some water. Yeah, look at that, that's pretty disgusting. I think we might need to filter that a fair bit, but oh well, we'll get that done. So now I've got here our lovely clean Tamar River water, sodium chloride solution, and we'll just filter that off now with a bit of paper towel. So that's looking a lot nicer now that that's been filtered. Hopefully it's pure enough to be able to react into sodium hydroxide. I've had to trim down the salt bridge a little bit, seeing as it kind of fell apart a bit, but I think this will do. We'll just have to add a little bit more water to the chamber where we're going to be making the sodium hydroxide. So we'll turn that on. See, we've got around 1.8 milliamps, kind of similar to what we had in the other cell, and we'll leave that going for about an hour, like last time. So I've had the setup running for about an hour, and it's a bit disappointing. We've only built up around 20 milliamps of current, even with 36 volts, which leads me to believe that this sodium chloride solution is not very concentrated, or the salt bridge might be bad now that we've used it once, and there's kind of, I don't know if you can see, there's a couple of bubbles through it. But look, it did work. You can see all the hydrogen bubbles on that electrode again. And if we test it with our pH paper, you can see that it has gone alkaline. I can also smell just a little bit of chlorine coming off the cell, which is also a good indicator that it is working. However, due to how slow the reaction is, and it really hasn't gotten very alkaline over that hour that we've had it running, I'd say definitely don't go for seawater to make your sodium hydroxide. Just go for regular table salt and stick it in the anode chamber, and you should do pretty well. But there you go. If you're running on currents as low as this, then obviously you'll need to run it probably for days if you actually want to generate any large quantity of sodium hydroxide, but it can be done. Now, to explain what's going on, I've drawn us a little diagram here. So I've got the two containers, the positive carbon electrode, negative carbon electrode, and the salt bridge, and we've got our solution of sodium carbonate here, and on the right we've got our distilled water. So when the current's switched on, what we get is a negative charge on the cathode and a positive charge on the anode. What this ends up doing is attracting, on the right side, it'll end up attracting all of the oppositely charged ions, so the positive charge of the sodium ions will be attracted to the negative charge of the cathode. So let's just draw that in. All of these sodium ions will be attracted through the salt bridge, which is an ion conductor like we said before, and end up in this chamber over here. Seeing as all of the negative ions are already over in this chamber, the positive, the anode, won't actually attract any negative ions from this chamber. The hydroxide ions and the hydrogen ions do actually move through the salt bridge as well, but it turns out that for every hydroxide ion that moves through the salt bridge, seeing as the cathode is splitting water into hydrogen, every time one goes through the salt bridge, there's another hydroxide ion generated on the cathode. Same goes for the anode. Every time a hydrogen ion leaves through the salt bridge, it ends up splitting water into oxygen, leaving behind hydrogen ions. So every time a hydrogen or a hydroxide ion actually goes through the salt bridge, it doesn't actually affect the number of hydrogen or hydroxide ions in either one of the containers. So I'll draw another diagram to show you what we're left with after this. So once the sodium ions have been dragged across into the right chamber, or with the cathode, the electrodes pick out the ions that are easiest to discharge. In the case of the cathode, that's the hydrogen ions. It's a lot easier to turn hydrogen ions into hydrogen gas than it is to turn sodium ions into sodium metal. So the hydrogen ions end up disappearing from the solution and just bubbling off the electrode as hydrogen gas. Same thing happens over here at the anode. Picks the ions that are easiest to discharge. In this case it's the hydroxide ions. So what it does is oxidizes the hydroxide ions into oxygen gas and leaves the remaining hydrogens as hydrogen ions. So we've got O2 bubbling off the electrode here, and you can see what we're left with is sodium hydroxide over here and hydrogen carbonate or carbonic acid over in the left chamber. If this reaction happened instantly, then this is what we get. We'd get a sodium hydroxide solution over on the right side with the cathode, and we'd have a carbonic acid solution over at the anode. However, seeing as the reaction does actually take time to progress, as we are making carbonic acid over here, it actually reacts with the remaining sodium carbonate. According to this acid-carbonate reaction, the carbonic acid will actually react with the leftover sodium carbonate to form carbon dioxide gas, water, and we're back to our starting point of sodium carbonate. So along with bubbling O2 gas, we'll also get carbon dioxide coming off as this reaction progresses alongside the actual electrolysis reaction. So what we end up actually having on the right here is, like what we said, a sodium hydroxide solution, whereas on the left we do actually lose all of the carbonate ions as carbon dioxide gas and oxygen gas, and we just end up with regular pH 7 water, like I said before, in the left chamber with the anode. I should probably state that this is actually by no means the real reaction that's happening as we electrolyse the solutions. In scouring the internet, I found absolutely no literature on using the carbonate ion with this kind of reaction, and so this whole thing about the carbonic acid reacting with sodium carbonate is just my theory. Feel free to correct me in the comments if you actually know what happens. I do think this theory is relatively sound, however, so I'll stick with it for now. When we use sodium chloride instead, we have the chloride ion over here. It's actually a lot more simpler than using the carbonate ion. Same as before, all the sodium ions will have migrated over to the cathode, and seeing as the hydrogen ions are easy to discharge, these will bubble out as hydrogen gas. But over at the anode side, chloride ions are actually easier to discharge on a carbon anode, so what we will get instead is the chloride ions being removed as chlorine gas. And what we'll end up with on the left is, same as before, pure water, and on the right we will end up with sodium hydroxide. Well, that's that. If you need to make some sodium hydroxide solution, all you need is a couple of carbon rods, a salt bridge, a couple of containers, power supply, and some kind of sodium salt. Making sodium hydroxide is actually only the start of the experiments that we can make with this thing. In the future we should be able to make stuff like bromine, iodine, all the halogens actually except for fluorine and astatine, make nitric acid even, various range of acids and bases, but until then, catch you next time.